All right, I talked to the TA, to Peter, and to Joe, and I guess there's a question that came up about what homework do you do? If you look at my last slide, these were the problems I wanted you to look at, okay? I will do most of these, all right? I think there's different ones that are assigned in the syllabus. Yeah. So the ones in the syllabus, that's what you're assigned to. Do them. Because that's what you'll be, I mean, they already have the exams made up, so that's what you'll be graded. I mean, yeah. But there'll be this stuff in there too, but just I'll do some of these with you, okay? All right. Now, again, the way I like to do this, I think we left off. We did this one the other day, right? Where we sketched it. So we're okay with this? This was just looking at the slope of everything? All right. So what I'd like to do is to start off. And again, the way I like to do this is, again, it's like you're practicing. You're getting ready for the marathon, all right? And what do you got to do? How do you practice? Keep doing what? Keep doing what you're doing. What does Michael Jordan got to do for the game? Practice. What's he doing? Shooting a J. Slamming a dunk. All right? So you got to do the problems. All right? So that's what I'm going to leave this side of the board for over here. This side of the board, I'm summarizing in the appendix what those integrals are. Now, again, you may say, why am I doing this now when I haven't had Calc 1, 2, or 3? Those are tools that we're going to use to solve the problems. Do you have to know all the internal workings of a compound miter saw to do crown molding? No, you got to know how to use the tool. All right? You will get to the insides of the tool when you need to learn it, and that's when you get to Calc 1 and 2, you'll learn out how do I go from this funny looking squiggly line to this time function. All right? That's what that is for. But right now, we're going to use the tool. We'll exercise the tool. We'll do problems with the tool. All right? Because after this, I'm going to get to differential equations, which you won't see that for another 2 years. But we're going to use it as a tool to solve more complicated engineering problems. Okay? So that's where we're going. All right? So get your gloves on. Let's get in the game. All right. So we're going to start off here. Oh, let me plug in. Too many pieces of technology here. All right, forgot to plug in something here. Lots of technology. I just like using this wireless guy. It's a little bit easier for me. And hopefully it helps you visualize what's going on here. Okay. We have a 30 microfarad capacitor. Little guy. Not a little guy, not a big guy, little guy. All right? And what we're going to do is we're going to get the current waveform. We're going to, now again, this is the symbol for a capacitor. When we have this little guy over here, that's the symbol for a battery. It's exactly the same thing as what's inside of here. It has a plus side and it has a minus side. Okay? That's the symbol for a battery. So what we're going to do is we're going to say, okay, we're going to say that the voltage across this guy, oh, did we do this? Yeah, we did this. Okay, all right, yeah. So this voltage is a time-varying voltage. The voltage is varying as a function of time. So all we're going to do here is if I need to find out what the current is, the current is given by I through C is C dV dt. Where is it? Right there. The current through the capacitor is the capacitance times the rate of change of the voltage. All right? So here what we're looking for, it's the capacitance, which is 30 microfarads, times the slope of that waveform. And again, we did this by eye the other day. We just said, you know what? This is a linear function. It has a slope of 5. Okay? It's 5. It's the, the change in y, or the change in v in this case, the change in x, or the change in t. So it's 10 divided by 2. It's a linear curve. Okay? So then we knew that since it's just a linear curve, when I differentiate this, it gives me a constant, which is this. And in the case from 0 is less than t, which is less than 2, we simply substitute in what that dv/dt is. Now again, this time axis over here is in milliseconds. So you got to be careful. This is in milliseconds. That's where we get the 10 divided by 2, which is the slope of this, and that 10 to the minus 3 comes in because this axis is in milliseconds. Okay, so you got to be careful about that, all right? So it's real short time intervals here. So we had from here to here, this comes out to be 150 milliamps. So this point right here is 150 milliamps is flowing into that capacitor. Then we keep the voltage constant. When the voltage is constant, dv/dt is what? What's the slope of a constant? It's 0. That's why this capacitor current drops down to 0. At this point, is the capacitor charging or discharging? Let's take a look at this. What's it doing here? I'm sending current in, it's charging it up. Then if I put a constant voltage on it, what happens to the capacitor? Let's look at the current. What's the current at this point? It's 0. If no current is flowing into the capacitor, what's happening to the capacitor? Is it charging or discharging? Neither. It's doing neither. Neither. It's not doing anything. All right? When I then flip the voltage around the other way, so the voltage is now, the slope of it's going negative, what's happening to the capacitor? It's discharging, and again, this value down here is minus 150 milliamps, so it's going out the other way. And then obviously when we get to this slope right here, the slope is 0, it's not doing anything. Right here, I'm charging it up again. So I do a charge, discharge, charge, stop, discharge, stop, and then charge it again. Okay, so that's physically what's going on. And again, the mathematics tells me what's going on also. Okay? All right, let's do another one. Now, in this case, I have over here on the left, it's not an independent voltage source. It's not like a battery. This is what we call an independent current source. What it does is it will maintain the current that it is. So right now we're saying, okay, I have in this case, it's a 50 millifarad capacitor. It has the voltage across the 50 millifarad. I can calculate the current or the voltage across. Yeah, at t equals 0. So what we have is we have across this capacitor. This capacitor has an initial charge on it, plus the minus of 10 volts. So it's already got a charge on it before we turn on the current. So now what we're going to do is we're going to calculate the voltage when the current flowing through the capacitor is 4t milliamps. Okay, so here's what we have. We go over and we say, okay, we have two relationships for the capacitor, but the capacitor current that we did the other day, I of t, is equal to V of t. Can you guys see that lettering in the back? Or does it need to be darker? Darker? All right, these pens are a little dry. Just, again, if you can't see something, let me know. I mean, there's no use in sitting back there and not being able to see anything. So don't hesitate to bring it up. All right, so we have V of t, V of t is equal to 1 over c, the integral from t0 to t of I of t dt plus v at t0. Now in this case, t0 is equal to 0 because we're doing this at t equals 0. So this now becomes 0, and this is 0. And that's 0 now. And the c is what, 50 millifarads? So v of t is equal to 1 over 50 times 10 to the minus 3 times the integral from 0 to t. Now, what is the current through the capacitor? It's given by this time function right here. We have I of t is equal to 4t milliamps. All right, and that's times 10 to the minus 3. So this is equal to, we're going to substitute that in right here. 4t and it's times 10 to the minus 3 because we're working with milliamps. And then I have a dt here. Everybody okay with that? Now, when I have, if you notice, this 4 and this 10 to the minus 3, they are constant numbers, are they not? They're just numbers. What can I do when I have an integral with the number sitting inside? Pull it out. Yeah, all right, so here what we're going to do is this is going to, now we're going to have 4 times 10 to the minus 3 divided by 50 times 10 to the minus 3, the integral from 0 to t of t dt. All right, now we look at it and say, is there anything over here in my toolbox that can solve that integral? Look over at the toolbox. Anything in my toolbox that looks like that over there? Is it a sine? Nah. Cosine? Nah. Exponential? Nah. T? Does that one work? Talk to me, Daddy. Come on. Does that one work? That's it right there. All right? Capisce? Comprende? Jindon? Nastrovia. All right, come on. So we got t right there. So now I'm going to use that formula. So now I can cancel out. The 10 to the minus 3's are gone, so I'm going to have 4 over 50. The integral is going to be 1/2 t squared. Now again, I'm going to start using, there's two notations you could use. I'm just going to use a straight line, a vertical line, because I have to evaluate that integral between those two limits, the lower limit and the upper limit. All right? So this becomes, now the 2 and the 4, that makes this a 2. So I'm going to have 2 over 50, and this is going to be t squared minus 0 squared. So this is going to equal 2 over 50 t squared. All right? 2 over 50 t squared. So we took this tool here and applied it to right here. Yeah. Oh, sorry, I forgot to add on. What's v at 0? 10. So this comes out to be 2 over 50 t squared plus 10. That's what it is in the end. So that's v of t. So again, given the current through there, increasing current, linear, 4t, the voltage will be developed across that capacitor that will be quadratic due to the integration, okay? It will be quadratic. Any questions? All right? Everybody okay? You look tired today. A little late night last night, huh? A little funky out there? Going to have a late night Friday night after Temple. Whoops, Memphis. We're going to a bowl game when we beat Memphis. All right, so there it is. So we bring that integral in. 2 over 50 t squared plus 10, which is 0.04 t squared plus 10. Okay? All right. Capacitors, again, the energy stored in a capacitor, we can derive it for you, but it's just 1/2 the capacitance times the voltage squared. That's how much energy is in there, all right? We don't have to worry about open and closed circuits about that yet. You'll get to that if you take Electrical Engineering Science 1. All right. Here we're going to do, all right, so now we have an independent current source that's going to be pumping current into this capacitor, all right? We want to find the current, the voltage, and the stored energy in this capacitor. So we need to find the current, the voltage, and the stored energy, okay? All right, let's go over and let's go to the blackboard, and let's get it done. Everybody okay? I can erase this? All right. All right. Let's see. For T, all right, so now what we have is if I draw this out again, here's the current, and the current is given by 24 e to the minus 40 times t. And here's my capacitor. And this capacitor has 3 microfarads on it. So that's 3 times 10 to the minus 6th. All right? 3 microfarads. All right, so now, and we're given that V at 0, we're given that the voltage across here, V at 0, is 0 volts. So there is no initial voltage on that capacitor. All right, there's nothing on there. All right, now, we want to find the voltage. The voltage for a capacitor, again, is given by V of t is equal to 1 over c, the integral from t0 to t of I of t dt plus V at t0. Now, in our problem, what is t0 equal to? 0. Okay? So now I'm going to substitute in what this current is. V of t is equal to 1 over c, which is 1 over 3 times 10 to the minus 6th, the integral from 0 to t of 24 e to the minus 40 t dt plus V at 0, which is 0. Yeah.
Can you write a little bit bigger, please?
A little bigger? I will certainly try. Yeah, yeah. That's the one thing I should have like a board up here. Maybe I'll order like a big board over here or something. I mean, here it's nice to get death by PowerPoint, but it's not easy to write off the board. But I'll write bigger for you, all right? Yeah. Again, any questions, don't hesitate, all right? So now we're going to have, let's bring the 24 out. Oh, got to write it bigger. See, that's my parochial school handwriting. Sister Eberhard, crack these knuckles to give me that nice handwriting. So now you're going to force me to go big on you. V of t is equal to, factor out the 24. And now we go to our toolbox. And we say, oh, wonderful toolbox, do you have a solution for me? And I do. Third one down. E to the AT. In this case, A is minus 40. Okay? So now we do this. So we're going to have 24 over 3 times 10 to the minus 6th. And then we multiply that by minus 1 over 40, because that's what A is. And then we have the integral gets evaluated as e to the minus 40t, and this gets evaluated between 0 and t. All right? So now I plug in what this is. So this gives me, let's see. Wait a minute. And this is in, be still my beating heart. You have to watch what are the units of the current? Hertz, that's frequency. Huh? Milliamps. Make a mistake here. What should be out here? Times 10 to the minus 3, because we're working with milliamps. All right? So in here, I need to modify this. E to the AT times 10. Actually, I need to do it up here. Right in here should be a times 10 to the minus 3. So then that gets factored here. I could do this then. All right. This will be 24 times 10 to the minus 3. All right? 24 times 10 to the minus. So we're good now, okay? Everybody with me? I just made a mistake on the milliamps. It's right here. And up here. So now this becomes minus 3 down here. Can you see it over there? No? All right, yeah. Oh, I'm thinking of this. You're right. You're right. Sorry about that. Yeah, this is minus 40. If I'm using this, yeah, got to use the tool right. Thank you. Very good. A is here. Yeah. Yeah. All right, where's your book? Is it 1 over A? I don't think it's 1. Huh? Hold on. My brains are a little scrambled. I teach 4 hours in a row when I'm doing this. So right now I got microprocessors on my mind. Come on, where's the appendix? Up. Index. 1 over. 1 over. 1 over A. So let's do this. How's that? Okay, we good now? Life is good. So this is minus 1 over 40. I had it right over here, I just didn't have it right up there. All right? Good to go? Okay. All right, so now we evaluate this. What this says is you have, oh, and I did the same thing again. This should be like this. See, sometimes, well, it's just evaluated between these 2 points. So V of t is going to equal, I'm going to need a number here, 25 divided by 40 divided by 3. Can anybody give me a quick? 24 divided by 40 and then divided by 3. All right? You'll give me a number for that. This is minus. What happens to the exponential, it becomes e to the minus 40 evaluated at the upper limit minus e to the minus 40 evaluated at the lower limit, which is 0. What do you get? Minus what? Minus 200. Oh, the whole thing, even with the 10 to the minus 3. Okay, minus 200. All right, so this becomes minus 200 times e to the minus 40 times t. And what's e to 40 times 0 gives me 0. And what's e to the 0? So this is 200 minus 1. And that's what the voltage is going to be. Okay, that's V of t. All right? Marvelous. Marvelous. All right. Find the voltage and find the energy stored. So we just went through it. There's 24. Whoa, 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 whoa. So then we just did the, in this case, instead of having 24, I took the milliamps and moved it into the decimal point there. So it made it 24, became 0.024. Then you got the 3 times 10 to the minus 6 down here. Here's V of 0. So then we just did, all right, so let's get all these numbers outside, get this outside the integral, take it out, e to the minus 40t left alone. Now we go over and say, okay, in my bag of tools, there it is over there. So I'm just going to pull it out. I evaluate it. So we get minus 200 e to the minus 40t minus 1. This is what we got there. Okay? What's that? This? Sure. How lab's going? All right? Doing the MATLAB stuff? What? Horrible. Why, what's the problem? It's a language. the language. You will get to use it. I mean, you'll get there. It is such, I mean, it's such a powerful tool. Yeah, it is really amazing. It's like learning C programming. You learn stuff like this, man. Don't share. Already? Oh, okay. Well, I teach assembly language, which is you're getting down to the ones and zeros, man. That's yeah. All right, you good? Good to go. All right. And there we have it. Just if you break that out, we're good. All right. All righty. So now let's just do another. All right. The current through a capacitor is given by 6. Now again, independent current source. So we have this guy. Oh, did you? Forgot to ask. Did you get it? Okay. All right. So now what we have is we have a capacitor with a current through it, and the current via 0 is 0. Determine the voltage and the power at t equals 2 seconds. All right. So here what we have is this is going to be 6 times 1 minus e to the minus t. So that's the time function that we have that's driving the current that is charging up this capacitor. Okay? And we're going to find everything at t equals 2. So now we have, again, we're looking for now it's going to equal 1 over c. This is a 0.5. This is a big capacitor. So it's 1 over 0.5. Now again, what's T0 in this case? We're starting off at 0 here. So we have no initial voltage across it. So this becomes 6 times 1 minus e to the minus t dt. All right? So we can factor the 6 out. The 6 comes out, so you got 6 over 0.5, and then I'm left with the integral from 0, this is 0 to t, of 1 minus e to the minus t dt. Okay? Now, I have the integral of 2 functions. It happens to be a constant function, and the other one happens to be an exponential function. When I have the integral of 2 functions, what can I do? You can split it up. So this now becomes, this is equal to 6. Now 6 over 0.5, this is going to give me a 12. So this is 12 times the integral from 0 to t of 1 times dt minus 12 integral 0 to t of minus e to the minus t dt. All right? Everybody okay with that one? Okal dokal? Yeah, go ahead. Yeah, I forgot. There's just a 0 out here. We'll just put a big old 0. Thank you. But you do have to add it if it's non-zero. Yeah. All right? So now we're going to, so v of t. Now, the integral, this is a number 1. I can pull this out or just neglect it. I have the integral of dt here. Here, I look down here, for those that can see it, it's k dt, where k is equal to 1. Well, that is equal to k times t minus t0. T0 in our case is 0. So this is equal to 12 times t minus 0. This minus comes out, so this is going to be plus 12. Now we have e to the minus t. So this gives me 1 over minus 1. And then I have e to the minus t evaluated between 0 and t. So this is equal to 12 times t from the first one minus 12 times e to the minus t minus e to the minus 0. So now v of t is equal to 12t minus 12, and e to the 0 is 1, minus 12 e to the minus t. This comes in here plus 12. Where at?
12t plus 12.
No, you got a minus sign out here.
Well, you already have
I got 12t here.
no, but it's actually minus 12t. Oh, you're minus 12 e to the negative e to the negative p, and then you swap the sign for whatever. That's what.
Am I okay here? All right, so I got 12t here. All right, here. Here's my 12t, minus 12 e to the minus t.
Should be the 12 before should be negative minus 12.
This one here?
Yeah, it should be minus 12.
Oh, from here.
Yeah.
All right, thank you. Yeah. Okay, got a sign mistake there. Thank you, sir. So that makes this minus, that makes this plus. That makes that plus, thank you. And that makes this minus. Man, keep me honest at the board. Attaboy. Keep an eye on it. You guys see that all right over there? Okay. Sister Aberhard, your nice fingers. Really cracked, man. All right. Now it has to find the power too. Well, the power. What did anybody see? Ever watch Star Trek? The power. Scotty, warp factor 5. Scotty says, I can't do it, Captain. I'm pushing the dilithium crystals as hard as I can. I don't have the power. All right, so power, P of t, is V of t times I of t. All you need to do to get the power is you're going to take this function here and multiply it by that function there. That's the power. All right. Now we have to evaluate this at t equals 2. So we have v at t equals 2. Now I need your calculators out. This is going to give me 12 times 2 plus 12 times e to the minus 2 minus 12. I need a number. Can somebody help me out here? The whole thing? 13.624? All right. We'll go with 13.62. Now, since I of t is equal to 6 times 1 minus e to the minus t, we're going to do this. I at t equals 2 is equal to 6 times 1 minus e to the minus 2. I need a number for that one. I need a number for that one. It's e to the minus 2. I'm sorry, I thought a little, it's e to, because I'm substituting it in right here. E to the minus 2. 5.19. All right, and to get the power at t equals 2, p at t equals 2, that's equal to v at 2, I at 2, which is equal to 13.62 times 5.19. Multiply those two numbers together. 70.69, and that's watts, because power is measured in watts, not in dilithium crystals. All right, so far? Good. Questions? All right. So when we cranked it out, boom. 12t, 12 e to the t minus the 12. You got 13.62, 70, so we got 70.66 watts. All right? All right. We okay so far? So far, so good. Is this boring you as much as it's boring me? Come on. Never had so much fun with your clothes on, man. All right? Oh! Don't record that, all right? That's going on YouTube, I know. My dean's going to love that. All right. No, just kidding. Come on, you got to have fun in this life. You got to laugh to keep from crying, man, all right? We're all hanging on by our fingernails here. All right. I think I'm going to come back to this one because I want to go to, well, we go to 1250 here, right?
Yeah.
Yeah, all right. Yeah, I got time to do this one. All right. Is it okay if I erase this over here? No, not yet? Is this good? Everybody? Not yet? Hold on. All right. And now we don't have class in here Friday, right?
Right.
You go to,
Friday.
huh?
Matt Lab on Friday.
MATLAB? Dr. Bai? Dr. Bai was a student of mine.
That explains
He was a
lot.
student of mine here. Yeah. His degree's from Temple. Well, his undergraduate degree, his master's and PhD are from down at Drexel. Does that explain a lot? Why?
Nothing.
Come on, don't speak ill of my boy. He's over in China right now. Breathing smog in Beijing. Oh. All right, we good over here? We finally good? All right. All right, so here again, now we're going to put in a current. We have a 4 millifarad capacitor. 4 millifarad sits over here. V at 0 is 10 volts, so it's initially charged. All right? We have a current. Now, this current is a time-varying current. It's not a direct current. It's an alternating current. Okay? We'll get to why. What's the difference between direct current and alternating current? DC and AC. What's coming out of that wall? AC. What's coming out of that battery? DC. Because it's fixed value. It stays constant as a function of time. It's called direct. A great story. Why do we use AC instead of DC?
Because it takes substantially less amount of material to transfer the current.
Not yet. This was an amazing battle that went on over this. You've heard of Thomas Edison, right? You heard of Edison? Edison wanted DC. He says, DC is going to be the way to go. And there was this other dude who worked for him. His name was Nikola Tesla. Anybody ever hear of Tesla?
Tesla coil.
You hear of the Tesla cars now? Like Elon Musk, the same guy that's doing SpaceX, the Tesla car. Well, it has nothing to do with the coil, but there is a Tesla coil. Tesla's working on it and says, Mr. Edison, you got it all wrong here. Got it all wrong. Edison goes, what are you talking about? He said, DC is going to be the way. And by the way, Tesla, you're fired. See ya. Tesla goes, all right. A guy picked him up by the name of George Westinghouse. You've heard of Westinghouse? Big time. When you see the K, or the KYW, the W's and all those little call names for radio stations, what's the W stand for? Westinghouse. Westinghouse goes, Tesla, let's go kick his ass. I mean, you're talking major bucks here, all right? I mean, lighten up the world. We will get to this when I get to the induction coil. The reason you use AC is because when I have a coil, you can walk around outside and you'll see them. You ever see transformers up on the telephone poles? There's a reason why there's a transformer up there. The transformer does this. I'll get to this problem in a minute. Don't worry about it. It has coils on both sides. This has a turn on, there's a number of turns here, N1, and then there's a number of turns on here, N2. When I put a current through a wire, as I showed you the other day, what happens around that wire? You get a magnetic field. So now I have a magnetic field around this wire, and if this is an iron core, if this is iron, it's going to induce a magnetic field inside of here. I'll call that magnetic field phi. If this is DC over here, now if I don't know if you've seen the experiment, if I take a magnet near a coil of wire and I start varying that magnet, what happens to that coil of wire?
Generate electrical charge.
You generate a current inside of there. That's why we call it an induction coil. You're going to, the magnetic field, it's an amazing thing. It's one of these things in nature. If I have a time-varying magnetic field near a coil of wire, it puts a current into that wire. So now what I have over here, if I have a time-varying, if I have a DC current here, I have a constant magnetic field here, will I get a current in the second coil? This is a constant magnetic field, not a time-varying one. What will happen? I won't get any current on this side. If I make this thing over here time varying, a sinusoid, 110 volts going at 60 hertz, I will then induce a magnetic field into this coil of wire of the same frequency, 60 hertz. What happens over in the second coil of wire? I'm going to put a little load out here. This could be your house. I'm going to now induce into this side over here another current. I will then get a current coming out of here. What this allows me to do is, based upon what these two turn ratios are, I can step this way up. So if I'm sitting at my hydroelectric power plant, I put a transformer there, and I step those voltages 50,000 volts, way up. Then I transmit it all the way down to your little house. Sitting outside your house is a step-down transformer that takes that high voltage, collapses it down to 110, which is coming out of your wall. You can't do that with a DC system. You can transmit the energy, but you can't transmit it very far. Mr. Edison built his first dynamo system in Manhattan. Why Manhattan? Why would you think? Everything's close, but what's in Manhattan? The money! Wall Street. He needs investors. All right? So he wants to put it there to light up all our houses. So he does it, and it's nice. He runs it down, and guess what? He starts getting near the edges of Manhattan. What happens to all the light bulbs? Again, you're running a wire. The resistance in a wire is a function of length. The more length you got, the higher the resistance. What's going to happen to the light bulbs that are really far away? They're dim or they're off. Tesla went to Niagara Falls, and he transmitted all the way across the state. Edison did not understand the concept of AC. It cost him his fortune. Amazing story. All right, that was my commercial break. Here. Before we get to that, and we'll get to this problem. I want to show you a little something here. I'll get to this problem. All right. Here we have a, we looked at this the other day, right? This guy. Here I have a current, no current, doesn't do anything here. A current will give me a magnetic field around here that will move these things around. And you can see it. If I have a compass, and this compass has, and really, so this is pointing north, and I have a wire running across here. If there's no current, this compass will be pointing north. It's going to point north. If I then run a current through it, the compass needle will no longer be pointed north. Again, an illustration that there is a magnetic field around the wire. So what we can do is, in order to increase this magnetic field, instead of having just a strip of wire, you make it into a coil. And and then you put an iron core inside of there. So now what you've got is a really good magnetic field. That magnetic field changed the world in many, many different. You don't have a generator, you don't have a motor, you don't have, I mean, you can go through lots of stuff. That's why we call it an induction coil. The induced part comes from the magnetic field. The coil part comes from, we wound it around something, all right? You can have all kinds of them. You can have circular ones wrapped around. Here's the one I'm showing you over here. This is wrapped around an iron core, laminated iron core. That's the induction coil. This is one of the early ones. This is an early transformer. Primary side, secondary side, all right? It's a beautiful thing. This is Faraday's. This was Michael Faraday's ring. He wound one side and then wound the other side. And then we can find out we can do work with this thing. Let me show you real quick some of the work we can do. This here is a battery with a little telegraph key, and there's an induction coil. It's in that white little thing right there. That has an induction coil. I run this wire all through a whole bunch of stuff here, and then I run it over to an identical device on the other end. All right? Solenoid's an induction coil.
Exactly the same thing on the other end. Switch, solenoid, DC cell. And then you have the transmission system in between. You can run this line as long as you want. So effectively, by hitting the key on one end, we're closing the circuit and energizing the coils actually on both ends. So you can see that the coils are pulling up and down. It actually gets transmitted down to the other end, and you can run this line.
So nobody's touching this thing over here. So this, when I click this, all you got to do is run that wire across the country. You have to have enough battery power, but now I can communicate over vast distances just using an induction coil and a battery. Samuel Morse said, man, I can make money off of this. Samuel Morse didn't invent the telegraph. Samuel Morse just invented the code, the dots and dashes. That's all he did, so have a good one. See you on Monday.